Hello and welcome to our presentation for BERC1213 Basic Electronics. I am Viven and together with my group mates will be explaining about our assignment focused on Zener diodes and transistor comparison between NPN BJT and N-channel JFET. So first of all, I want to explain about what is a Zener diode. A Zener diode is unique because it allows current to flow in reverse once a certain voltage called Zener voltage is reached. This makes it perfect for voltage regulation in circuits. Next, I would like to explain about Zener diode theory. In forward bias, it behaves like a regular diode, but in reverse bias, once the Zener diode voltage is reached, it's conduct without damage. This property allows it to maintain a steady voltage even if the input is varies. One, I would like to explain about practical application of Zener diode. For Zener diodes are used in voltage regulators, over voltage protection, waveform shaping and voltage reference circuits. They play a key role in keeping electronics safe and stable.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Heiqal bin Rosli. My matrix number is B1224100648. Today I will present a Zener vs a valence breakdown. Zener and equivalent breakdown are two ways a diode breakdown when too much reverse voltage is applied. Zener breakdown happen at low voltage below 5.6 volt due to electron tunnel, and it is very accurate. A valence breakdown occurs a higher voltage above 6 volt when fast moving electron hit atom and creates more electron, causing a chain reaction. It less reverse but still useful, especially in high voltage protect circuit. For slide 6 is a Zener symbol and a packaging. The basic is that Zener diode symbol looks like a regular diode but with band end on the bus side. This means the basic diode symbol is a triangle point to a straight line, but Zener diode has a small angle wings on the line, showing it has special reverse breakdown behavior. The band's end represent Zener's special breakdown behavior. This shows that the diode can conduct in a reverse bias after reach its Zener voltage, unlike normal diode that block reverse current. The cathode is marked with a band. It must be connected to the positive terminal in reverse bias. For the example, if you using a 5.1 volt Zener diode for voltage regulation, you connect the band cathode leg to the positive voltage and the other leg anode to ground. The diode will only conduct if the voltage goes above 5.1 volts in the reverse. Common package, glass body, through hole and surface mount SMD. This a simple circuit using a Zener diode to keep the voltage steady across the load. In this example, a 20 volt DC power supply is connected in a series with a 250 ohm resistor and 50 volt Zener diode, which is placed in a reverse bias. A 1K load resistor is connected in parallel with the Zener diode. When the input is 20 volt, the Zener diode conduct in reverse once the voltage reaches breakdown value of 15 volt. Keep the voltage across the load clamped at the 15 volt. The extra 5 volt is dropped across the series resistor limited current and protect the diode. This is a Zener regulator calculation. The component is input voltage Vin 20 volt, Zener voltage PZ 15 volt, series resistor 250 ohm and load resistor 1000 ohm. Method 1, voltage across the series resistor. VR equals to Vin subtract VZ 20V subtract 15 volt and we get 5 volt for VR. Method 2, total current from the source through 250 ohm resistor. I total VR divide R. VR we get 5 volt and the resistor is 250 ohm and we get 20 milliampere. And next, the method 3, current through the load 1k ohm resistor. IL equals to VZ divide RL. 15 volt divide 1000 ohm and we get 15 milliampere. The lastly is a current through the Zener Diode. IZ equal I total subtract IL. 20 milliampere subtract 15 milliampere and we got 5 milliampere. That's all from me and I will pass to my fellow friends. Thank you. Assalamualaikum.
Thank you for your part, Heiqal. Good morning to everyone. My name is Dineash and Aqil, and my part is I want to talk about advantage and limitation of Zener diode. So let's talk about the advantage first. One of the advantage is it is simple to design and use. This is because the basic voltage regulation circuit, like using Zener diodes or resistor divider, don't require complex components or advanced design knowledge. Second, it is inexpensive and also small. These circuits use minimal components such as resistors, diodes, or sometimes capacitor, which are cheap and widely available. Third advantage, it offers good voltage control for low power circuit. They are effective for maintaining a stable voltage in circuit that draw a small constant current. Next, let's talk about the limitation. The first limitation is it is not ideal for high current or power application. These methods are not efficient or reliable when powering loads that require large current. Second, it can be affected by temperature. The performance of diodes and resistors can vary with the temperature. The third limitation is it is less accurate than dedicated voltage regulator. Compared to the IC-based voltage regulator, simple design offer less precise voltage control and can vary with the load or input in fluctuation. The last limitation is it needs a careful resistor choice to prevent overload. If a resistor aren't chosen based on the correct power ratings and load correct calculation, they can overheat or fail. Next, let's talk about the BJT and JFET introduction. So, BJT 2N3904 is a bipolar junction transistor, which is controlled by the base current, which means the base current determines the collector current, which have three terminals. First terminal is base, which control current flow. Second is collector. It is a main current path. The third one is emitter, which is a common reference point. Now let's move on to the JFET 2N5454. JFET is a N-channel junction field effect transistor. That's voltage control where the gate voltage controls the drain current. Next, let's talk about the BJT circuit 2N3904. This BJT circuit is powered by a 12-volt DC supply and consists of voltage divider which have two resistors. The first resistor is 2 kilo ohm and the second resistor is 33 kilo ohm. Both of these resistors are set to the base voltage. And then we also have a collector resistor which is RC, which is set to 6.8 kilo ohm. Third, we have an emitter resistor which is RE, which is set to 680 ohm. And also to measure voltage at base VB, emitter VE, and collector VC, we need to build this and simulate the circuit in the multisim. Next part, let's talk about the BJT calculation. So for the first calculation, which is base voltage VB, it is measured as 1.19 voltage. This is set by the voltage divider formula, which is VB is equals to VCC multiplied with the second resistor divided by sum of the first and second resistor. So after do this calculation, we will get the answer of 1.9 volt. After that, we need to calculate the emitter voltage, which is V. The calculated answer is 1.3 volt. To calculate this, we need to use the formula of emitter voltage, which is VE is equals to VB minus VBE. For the VB, we already get from the previous answer, which is 1.9 volt. And then VBE is a constant value of 0.6 volt. We minus 1.9 to 0.6, we will get 1.3 volt, which is the emitter voltage, VE. The third part is we need to calculate the emitter current, which is IE. The calculated answer for the emitter current is 1.19 milliampere. The formula we use, IE equals to VE divided by RE. The VE we get from the previous answer, which is 1.3 volt. We divide with the RE, which is the constant resistor value in the circuit, which is 680 ohm. So we divide 1.3 volt to 680 ohm, we will get 1.91 milliampere. This current flow from emitter to collector. For the last part, we need to calculate the collector voltage, which is VC. The calculated value for the VC is 8.18 voltage. To calculate this answer, we use the formula of VC is equals to VCC minus IC times with RC. The VCC is a constant value from the circuit, which is 12 volt, and then IC we get the answer from the previous calculation, which is IE. This is because the base current is very small, so we assume IC is equals to IE. That's why we use the previous answer, which is 1.91 milliampere, and use it as the IC. For the RC part, RC is a constant value in the circuit, which is 6.8 kilo ohm. So we calculate all this, use this formula, and we'll get the final answer of 8.18 volt. That is the collector voltage of VC. That's all my part. Let's continue to the next part. Thank you.
Hi, Assalamualaikum. My name is Muhammad Aqil. So my part is BJT simulation and graph. This slide shows the simulation of our BJT circuit. We plotted a graph of collector current IC versus collector emitter voltage VCE. As VCE increases, the collector current also increases, which is the typical behavior in the active region of BJT. This confirms that our circuit is working correctly. The simulation result also match our manual calculation, so we know our analysis was accurate. Next, let's talk about JFET circuit 2N5454. So this slide shows the JFET circuit we built using the 2N5454 transistor. We used a 12 volt DC supply. The gate was biased using two resistors, which is 2k ohms from VDD to gate and 33k ohms from gate to ground. We also add 6.8k ohm resistor at the drain and 618 ohms resistor at the source. We measure three important values, VGS, ID, and VDS. These readings help us check if the transistor was working correctly. Like with the BJT, we also run a simulation to confirm the behavior. So next, let's talk about JFET calculation. In this slide, we show the manual calculation for the JFET circuit. The gate voltage VG was 0 volt because of the voltage divider. The source voltage Vs was measured as 1.3 volt. So VGS equal VG minus Vs, which gives us negative 1.3 volts. Next, we calculate the drain current ID by dividing Vs by the source resistor. 1.3 volt divided by 618 ohms, which gives us around 1.91 milliampere. Finally, to get VDS, we use VD minus Vs. VD was 8.2 volt, so VDS equal 8.2 volt minus 1.3 volt, which is 6.9 volt. This result match our simulation, proving that the transistor is biased properly and operating in the active region. So next part is JFET simulation and graph. This slide shows the DC transfer characteristic of JFET. The graph shows how the drain current ID increases with the drain source voltage VDS at the beginning. After a certain point, the current level off, which indicate the JFET is in the active or pinch-off region. It's also showed that when the gate source voltage VGS become more negative, the drain current decreases. This is an important behavior of a JFET, where the current is controlled by the gate voltage rather than by current, like in a BJT. The simulation circuit on the left support this behavior. The value measured during the simulation showed that the JFET is correctly biased and operating in the active region. This confirms that JFET can effectively control current using voltage at the gate, making it a good choice for amplification and signal control in the electronic circuit. And now I will demonstrate our BJT circuit using the simulation. As you can see, the circuit is powered by 12 volt PCB supply. We use a standard NPN BJT with biasing resistor. And now I will run a simulation. You can see the collector current IC increasing as the collector emitter voltage VCE goes up. This confirms the transistor is operating in the active region. And now I will show our graph. This matches what we saw in our graph and manual calculation. When VCE increases, IC also increases as expected. This proves the transistor is properly biased and working correctly. That's the demo for the BJT circuit. And next, I will demonstrate the JFET circuit using the 2N5454 transistor. The circuit uses a 12 volt DC supply. The gate is biased using two resistors in a voltage divider. The drain and source also have resistor to help control current. Now I will run. Here you can see the measure value. VGS is around negative 28.6 millivolt. VDS is about 3.8 volt, and ID is 3.06 milliampere. Now I show our circuit. Right, this shows the JFET is operating in active region. As expected, it controls the current using voltage at the gate. This simulation matches our calculation and the behavior we expect from a JFET. That's all for the JFET circuit demonstration. So that's all from me. I will pass to my friend. Thank you and Assalamualaikum.
Hi everyone, my name is Jeevan and thank you for the Aqil for the his explanation. And okay, and I will explain about what is different BJT and JFET. Okay, D is stable for the difference. As we know, BJTs are current control with low impedance, great for switching and amplifying. JFT are very voltage control, offer high input impedance, and are preferred for the low noise application. And next is discussion based on result. As we know, our simulation matched with theory. The BJT's behavior was dependent on base current, while the JFT was controlled by gate voltage. This helped us to understand what is different between these two transistors. All right. And next is our final conclusion. As we know, we successfully built and test both transistor, which is BJT and GFT circuits. We verify important parameters and gain on hand experience while we doing the circuits. And we also do calculation and simulation. So it's very helpful for our upgrade our knowledge because we do and experience. Alright. Okay, and this is our reference and datasheet and YouTube link. So our source included datasheets on semiconductor and visual simulation with tools like Multisim,
So that's
Tinkercad,
all for our
and
presentation
notes
today.
from the
If you have any question, make sure to
subject
comment it in the comment
our
box.
subject that
And make sure to
is
like and
our
subscribe
Jeevan.
our channel
Okay,
if
that's all
this
from
channel
me.
helpful
Thank
for
you.
you. Thank you so much for watching. See you all. Have a nice day.